We're looking at the Unit 1 NAB, and this is question 6, which is outcome 4, and we're going to look at part A first. So we're asked to sketch the curve with equation y equals x squared over x minus 1. The question is nicely broken down for us, so the first thing it's asking for is the two asymptotes and how they're approached. So we're going to first of all be looking for a vertical asymptote. And remember, this occurs when our denominator is 0. So x minus 1 equals 0, x equals 1. Okay, we have the vertical asymptote. Now we're going to look for horizontal and oblique. Now, first thing I'm noticing is I'm looking at my function and I see that the order of the numerator is higher than the denominator. So it's top heavy. I'm going to have to do some algebraic division. So I'm going to set it up with x minus 1 into x squared. X times x would give me x squared. It would give me x squared minus x. So if I take that away, x squared minus x squared, nothing. 0x minus negative x gives me positive x. I would multiply that by positive 1 to get x. So I've now got x minus 1. X take away x, nothing. 0 take away negative 1 leaves us a positive 1. So now I can rewrite this function that we started with here. I'm going to rewrite it as a partial fraction. I can already see my oblique asymptote in the answer, but I'm going to write it as partial fraction to start with. So y equals x plus 1 over x minus 1. And remember, when we're looking for the non-vertical asymptotes, we're looking for what happens as x approaches infinity. And you can see that this part here would just disappear as it approaches infinity. So our actual oblique asymptote is y equals x plus 1. So we've completed part A in that we've found the two equations of the asymptotes. We haven't yet addressed how they're approached, but I'm going to leave that until we're actually drawing the sketch, and then we'll look at how they're approached. Second part of the question is asking us to find the intersections with the axes. This is pretty easy, so to find what intersects with y, we'll make x equal to 0. We're going to substitute that in. So we've got a 0 on top, so straight away we know that y is also going to be 0. So we have an intersection at 0, 0. Are there any other options for y being 0? Well, y is 0 when x squared is 0, which means that only occurs when x is 0. So this is our only point of intersection, is 0, 0. Okay, the third part of the question asks us to find the turning points and justify their nature. So this is just like in higher, so we're going to be differentiating the function. Now I want to go back and just the way we rewrote the function for part A. Now we could just differentiate in this form. We could use our quotient rule, or we could bring the bottom up, use our product rule, but it's generally easier if we've already rewritten the function as a partial fraction. It's easier to use that, so that's what we're going to do. So our function was x plus 1 plus 1 over x minus 1. So I'm just going to rewrite that as x plus 1 plus x minus 1 all to the minus 1, and then I'm going to differentiate. So it's going to give me 1 minus x minus 1 to the minus 2, which is 1 minus 1 over x minus 1 all squared. To find my stationary points, I need to set that to 0. So I can rearrange to see 1 over x minus 1 squared equals 1, which means that x minus 1 all squared must equal 1. So x minus 1 could be plus or minus 1. So the two options are x equals 1 plus 1, which is 2, or x equals negative 1 plus 1, which is 0. So I have my two x coordinates of my stationary points. I'm just going to calculate the y values. If my x is 2, I've got 4 over 1, which is 4. So I'm going to have a turning point 2, 4. When x is 0, my y is going to be 0. So that's my second turning point. Now I actually recognise this coordinate. It's come up already. It was a point of intersection. So that one point of intersection is also a turning point. Now we're asked to find the turning points and to justify their nature. We could of course use a nature table to justify the nature, but what we're going to do is take the second derivative. And remember that in addition to allowing us to check the nature of our stationary points, this also allows us to check for any non-horizontal points of inflection. So our first derivative was 1 minus 1 over x minus 1 squared, which is 1 minus x minus 1 to the negative 2. So if we differentiate that, we get positive 2 x minus 1 to the power of negative 3 times 1, which is the same as 2 over x minus 1 all cubed. Now to check the nature, we're going to just substitute in the values for our stationary points. Our first stationary point has the x value of 0. And if we put 0 in, we get 2 over negative 1 cubed, which is a negative 2. The second stationary point occurred when x was equal to 2. So if we put that in, we get 2 over 2 minus 1 all cubed, which is positive 2. So for our negative 2, we have a maximum turning point at 0, 0. And our positive 2 tells us we have a minimum turning point, and that was at 2, 4. So we've now got all the pieces of information. What we're going to have to do is put it together in a sketch. Before we do that though, we're just going to check if this derivative that we've just calculated here, if we make that equal to 0, just to check where the non-horizontal points of inflections are, we can see, because we've got a constant on the top, this will never be equal to 0. So there are no non-horizontal points of inflection. Okay, so let's put it all together in a sketch. I'm going to draw in my axes, and first of all I'm going to draw in my asymptotes. So I've got 1 at x equals 1. I'm going to put that down here. When you're doing these diagrams, just label as many things as you can. So x equals 1, obviously that point there is 1. I'm going to also draw my other oblique point, which is going to be somewhere along here. Obviously you're using a ruler. It's cutting there at 1. It's going to cut here at minus 1 because it is y equals x plus 1. I also know that I have a maximum turning point at 0, 0 and a minimum turning point at 2, 4, which is going to be here somewhere. And I'm going to just check my values. And remember the oblique one, we need to look at what's happening as x approaches from the left and from the right. And the same on the horizontal, the vertical one. So as it approaches from the left, I'm going to look at values less than that. So that's going to be, let's say, -2. And then I want to try and find a value that's in here somewhere. So I'm going to look at -0.5. I also want to see if there's anything going on in here. So that's going to be +0.5. And I want to check here whether I'm in this area here or this area here or both. So I'm going to check for 3/2. So if I'm at -2, I'm going to write what my function is so that I can work these out. So my original function was y equals x² over x - 1. So if I put in a -2, I'm going to have 4 over -3, so I'm going to have a negative answer. If I put -0.5 in, I've got 1/4 over negative, so that's negative. So leading up to this point and after this point, I've got negative values. So my curve in this area here is always going to be under the x-axis. So I must be coming in this direction. I know that I'm turning here. I know that that's not a point of inflection, so I know that I'm actually going to be going down in this direction. But my -0.5 checks and tells me that I'm going to be in negative here as well. So I'm just going to draw that part in. I'm going to put in, remember we're trying to put as much information as possible, so I'm going to put in my turning point of 0, 0. This pen's not very good for writing small things, so just your diagram should be tidier than mine. Then I'm going to check this side, the right hand side of our vertical asymptote by checking for 3/2. When I put 1/2 in, I got 1/4 over negative, so that was a negative. When I put 3/2 in, I'm going to get 9/4 over positive over positive is going to give me positive. So in this area here, I need to be positive, so I need to be above this axis, which means I'm in here, I know I have a turning point there already. So I'm going to go something like this. Turning point is 2, 4, and that's me done. This is a 9-mark question in the NAB, so take your time with it. Make sure you go through all the steps, and when it comes to drawing your diagram, just put as much evidence as you can onto the diagram, and be sure to show any working out you're doing that helps you to show how your curve is approaching the asymptotes. Okay, hope this helps.